right into it. Um, so today's topic is a little bit vast. Um, if some of you have attended my previous series of lectures, I have talked very extensively about different technologies that are used in the oil field industry, primarily in oil and gas drilling, in completions, in fracking. Um, and this is just a continuation of that whole discussion. And I wanted to have to give you guys a little bit of flavor on different type of technologies that are used in drilling, primarily directional drilling, but we will also going to talk about PDM, which are positive displacement motors. We are going to talk about different type of drilling techniques, and we are also going to talk about um, types of drill bits. Um, drill bits, I'm going to very briefly touch upon the drill bits. We are not going to go very extensively in that because we just won't have enough time today, but it would give you an appreciation about how far the industry has come along over the period of 1 century. All right. At the end of this training session, you should be able to identify different type of rigs. So you will be able to identify onshore rigs, offshore rigs, different type of offshore rigs. You will be able to appreciate the directional drilling and how important of a role it actually plays in today's energy scenario. And you will be able to uh, figure out some of the directional drilling techniques as well as the different type of drill bits. All right. Why drilling is so important? Uh, it is our primary way of accessing these energy sources which are buried deep inside the earth. Over the period of time, the drilling techniques have evolved and uh, it has become more efficient, less carbon intensive. That means there are less emissions associated with drilling operations, but there are also less environmental risks. Obviously, these type of operations do come with environmental risk. I'm not going to discount that, but with the passage of time, the industry has become more conservative. There are different regulatory as well as best practices that are in place to ensure that the damage to the environment is minimal. Just a quick timeline of where it all started. Drake well was the first successful well that was drilled in USA. It was a very shallow well which used to produce close to 25 barrels of fluid per day. But as we started becoming more and more experienced and the rotary drilling operations started becoming more matured, we were able to drill at deeper depths. And by 1901, the average production per well had increased to almost 48,000 barrels per day. But in 1900s, when the large oil fields were discovered by the Anglo-Persian Oil Company, then there was a certain boom of oil which started being used in the internal combustion engines, and with Navy flotillas becoming larger, and with the internal combustion engines and vehicles coming in, it was deemed that a steam engine which was being run by coal is not going to be efficient. It's not going to be plausible to have steam engines, especially on the vehicles. So the demand for the fuel started increasing. And 1950s, oil became the first and foremost fuel in the world and became one of the topmost commodities that started being traded on a global level. Now, when we talk about the oil field industry, there are two things which you will hear quite often. One of them is upstream, one of them is downstream. Sometimes people get confused, what is upstream, what is downstream. I'll try to make it a little bit easier for you. Usually when we talk about upstream, we are talking about exploration and production. But as we start talking about processing and refining, we are talking about downstream. So a lot of times you will hear about upstream developments and downstream developments. Downstream is more towards the petrochemical refining when you start dividing that hydrocarbons into more like ethylene, ethanol, uh, uh, gasoline, diesel, and that's where you actually start utilizing them, not only in terms of as a fuel, but also in chemicals and polymers. So exploration and production today topic is more towards towards the upstream sector. It's more towards the exploration and production. In our subsequent lectures, we are going to talk about processing and transportation and storage. Reserves versus, give me a second. So reserves versus producers, there are two different concepts. One is proven reserves, and one of them are the producers. Reserves means that they have drilled appraisal wells and they know what is the quantity of hydrocarbons in those areas. Those are proven reserves. That means certain areas in the world have more proven reserves than the other areas of the world. For example, when you see on the right-hand side, you can see that the Middle East has the highest proven reserves of oil, around 753 billion barrels of oil per year of proven reserves that they have. This is followed by North America, primarily US and Canada. In Canada, it's primarily oil sands, while in US, it's primarily shale oil. And then in South America, and so on and so forth. But in terms of producers, the biggest producer in the world is Saudi Arabia, followed by Russia and US. These are the three biggest producers. Russia and Saudi Arabia are part of the OPEC, which is a particular community of oil producers in which they actually try to regulate the oil prices while accessing resources. So in terms of accessing resources, it's first and foremost, whenever you are trying to extract oil and gas, hydrocarbons from subsurface, it's very important how you are addressing accessing of resources. Accessing of resources is where we have vertical drilling. Accessing of resources is where we have directional drilling. Both of these are fundamentally slightly different concepts, in a way that vertical drilling is something which is very matured. When we first started drilling oil for oil in late 1800s and early 1900s, vertical drilling was the method of choice just because it was less complicated, it was easy. It resulted the availability of tools, the availability of technology at that point of time only supported vertical drilling. That means you will be right on top of your reservoir. You will have a bottom hole location, which is almost same as the surface location. That means you are directly on top of your reservoir. You will drill directly straight and you will access the hydrocarbons. But over the period of time, as more of these hydrocarbons were getting extracted from the subsurface, vertical drilling became not the method of choice, in a way that sometimes, in a lot of scenarios that we are going to discuss in the subsequent slides, it is not easy to drill vertically, just because sometimes there are built up areas, there are cities where these reservoirs are. There could be other geological factors that will restrict you from drilling directly vertically. Drilling vertically means that when you have to move from one well to one well, you will have to move your rig, which becomes a very, very expensive process, especially when you are drilling in an offshore kind of scenario. So drilling vertically may not be a method of choice, as we are moving into a new age of energy extraction. This is going away and away. Now, directional drilling, in which your bottom hole location is way different from your surface location. That means you will go vertically, or you will go slant, and then you will access your hydrocarbons. And there are a couple of reasons for it. Number one is horizontal wells do afford you a better production. You can keep your rig at the same location, and then you can drill multiple wells, and you can access different formations and different hydrocarbons. The other reason for this is what you see right over here. You have a land rig, which is much cheaper to operate, has a much less complexity, and you will be able to access a resource which is in a shallow water, which if you will have to drill vertically, you will have to use a drill ship or a semi-submersible or a jackup rig. So scenarios like these actually makes us prefer directional drilling. And as we are going towards shale production, and you might have heard about this, directional drilling is a method of choice. We don't do vertical drilling in the shale production, just because shale is a very difficult formation to access. And to make the shale production economically feasible, you have to have a well that is directionally drilled. Different type of oil rigs. In this section, we are going to talk about different type of oil rigs and what are their different complexities. Land rig is something which you might have seen or you might have experienced over the course of your time. They can actually drill quite deep, almost 25,000 feet, which is around roughly 7 to 8 kilometers. And they are very mobile. They can be moved from place to place. They can be assembled and disassembled very quickly. Usually for the deployment of the oil rig, you will need some sort of lease preparation to deploy it. Usually the rig up time and rig down time can take a couple of days. Jackup rigs are primarily for shallow waters, not for very deep, aggressive drilling applications. They have lift legs, which you can see over here, that are resting on the seabed. And then you have surface mount BOP. That means your BOP is going to be right on the drilling floor. And then they are very feasible for 400 feet of water depth, not more than that. And then drilling depth is usually around 30,000 feet, which is around 5.5. Semi-submersibles, these do not have legs that are resting on the seafloor. They have pontoons, effectively, which are dynamically positioned in a way that the pontoons will have a water level. And as you have to stabilize your rig, you will increase or decrease the water level on those pontoons. And what's going to happen is that you will have thrusters around the rigs that will actually dynamically position it so that it doesn't move, and it can actually drill quite deep. They are more feasible for seafloor wellhead connections. That means you will have a subsea structure, and there's a possibility that your BOP will be light there on the seabed. They are more feasible for 1,000 to 3,500 feet of water depth, and they can drill all the way to 35,000 feet of drilling depth. And finally, we have drilling ships. These are used for more deep subsea applications. They are huge. They are very difficult to operate, and just difficult in terms of it. They are very expensive to operate. And I can tell you that a typical day rate of a drill ship can be in almost $900 to $1 million of day rate per day. So they are very expensive to operate. So they are usually used in harsh environments, in Arctic environments, environments in which you have rough seas, you have deeper drilling depths. So they can almost drill to up to 10,000 feet of water depth and 30,000 feet of drilling depth. They are usually used with the subsea infrastructure. That means you will have subsea compression trees, you will have subsea BOPs, you will have a subsea tree. They are self-propelled with dynamic positioning, so they will have thrusters all around the ship, and they will be able to dynamically position it with the help of a GPS, a very, very accurate GPS system. Downhole drilling operations. In a typical drilling operation where you have a vertical, this is what we call a bottom hole assembly. Whenever I'm talking about a BHA or a bottom hole assembly, this is what I'm talking about. Essentially, what happens is that you will push the mud from the surface, and then you will have a rotating rotary table at the top of the rig that will rotate this entire bottom hole assembly. We will be injecting mud from the top, and there are a couple of reasons why we inject mud from the top. Number one is to ensure that you have some pressure on the formation. Effectively, what you want is to have that pressure on the formation so that formation fluids do not come into the borehole. And the second thing is that you want to remove those cuttings. So the cuttings that are being that dislodge from the drill bit, They need to be traveled. They need to be moved to the surface so that you can clean them. Uh, Otherwise, they will just accumulate around the drill bit, and then it can actually damage the drill bit as well as overheat it. Uh, the other reason is that the drilling mud also provides the lubrication for the drill bit so that it can actually have a higher rate of penetration uh, while reducing your cost. Because as you can see that time is money. If you can reduce your drilling time by increasing the ROP, you can actually reduce your uh, uh, cost of drilling per well. There is another thing which is called cake. Cake is essentially a packed amount of mud on the borehole. Uh, Essentially, what happens is that as you start drilling along, there will be a layer of mud that will form around the borehole, and it plays a very important role. It prevents the borehole from collapsing. That means you don't want the drill bit to drill and then your hole collapses on top of it. So the drilling mud actually helps in making that drill mud cake so that you can actually have that compact mud around the borehole so that prevents it from collapsing. Now, as I mentioned earlier, that the pressure is very important where you are drilling. There are two types of drilling. One is called uh, overbalance drilling, and the second one is called underbalance drilling. We are not going to discuss the two types of drilling methods. Essentially, overbalance drilling, and underbalance drilling have their own pros and cons. Uh, we sometimes use underbalance drilling more. Essentially, there are a couple of downhole factors that you need to be aware of when you are drilling. Number one is that when you drill through different formations, every rock formation will vary in terms of porosity and permeability. That means there will be some mud lost in that formation. And it will vary from formation to formation. And these formations are under immense pressure. Sometimes this pressure can actually hurt your drilling operations. So you have to be aware of your pressure at all times. That's why in the doghouse or in the drilling control center, they are always looking at the pressure because they are trying to predict what type of formation they are actually going through. And controlling formation pressures are key to safe and profitable wells. Because you might have heard about a phenomena which is called blowout. Blowout is effectively what happens is that you are drilling and then you hit a zone, hit a formation where there is a high formation pressure. That means your drilling mud pressure is lower than your formation pressure. Now there is going to be a delta or pressure differential between the formation pressure and your drilling mud pressure. What will happen is that the formation fluid will try to go inside the borehole. This is what we call essentially a kick. So the kick can be actually felt in the surface because what will happen is that the fluid that is coming at the top will have more of that unwanted influx of formation fluid and less of the drilling mud. So you will be able to detect the kick on the surface. So it's very important because if you will not control the kick, it will result in a phenomena which is called blowout. In a blowout, what essentially happens is that you will have an uncontrolled influx of this formation fluid into your borehole. You will be trying to inject mud at a higher pressure, but it's too late because you didn't control the kick. Now, what will happen is that formation pressure will go all the way to the surface, and it will result in a blowout. And an uncontrolled blowout can result in a loss of well integrity. That means you won't be able to. You will have a component which I have talked about in my previous, or not a component, more of a system on the surface, which is called blowout preventer, which can actually control that blowout. But if you don't control the blowout, that's where the environmental disasters will happen. And if the blowout can easily turn into a fire that can engulf the whole rig. So keeping a note of your pressures is very important and recognizing those warning signs. There are a couple of ways in which you can actually recognize those warning signs. You can recognize your kick, primarily because of historical data. So you might have drilled different wells in that particular area. So you would know the pressures in that area, different formation pressures as you will drill along the trajectory. You will have the seismic data as well. So seismic data can actually tell you which formations are at which depth, and effectively they can tell you, you can actually do a lot of predictive modeling to predict what is the downhole pressure at those particular depths. And also geologically, you will have a different type of formations. You will have salt domes, you will have shale formations, you will have different type of these formations, and you can actually have a very good idea about what is the geological properties of these formations, and you can predict the pressure influx in those formations. There are a couple of pressure increase indicators. Number one, your rate of penetration or ROP will change. It will increase or it will decrease. If it will increase, that it actually means that you are actually going through a very permeable zone. But if it will decrease, that means you have hit a rock formation. It's very difficult, and there is a possibility that there is differential pressure, which is actually pushing your bottom hull assembly at the top. Well flows with the mud pumps off. That means, so mud pumps, as I mentioned earlier, you are constantly pumping mud downhole for your drilling ops. When you have a kick, what will happen is that you will have a well flow without the mud pumps. So you can turn off your mud pump and you will have a well flow. And that actually tells you that you have actually hit a formation where the formation pressure is high. And then change in the mud properties. So that is something which they are doing because it's a very systematic way of checking for the formation fluid. They are constantly checking their mud formation properties. So the mud that is coming back to the top side, they are doing chemical analysis on that mud. So there is a lab on the drilling rig, which is actually checking for the mud properties. And they are looking for hydrocarbons. They are looking if there is a huge influx of hydrocarbons in this mud. And similarly, increase formation pressure readings of the logging graph. There are logging tools available on the rig floor in which we are looking at the formation pressure. One of the techniques that is used very exhaustively right now is called MWD and LWD. MWD is called measurement while drilling, and LWD is called logging while drilling. Essentially, before your drill bit, you will have these big electronic assemblies which are logging formation pressures in real time and giving you that information through telemetry on the top side. So they are actually telling you, okay, if I'm passing through a certain formation, what is the pressure? So this is becoming more and more common. A lot of companies actually use the LWD and MWD tools. Cause and effect. So insufficient fluid density, which is one of the causes of the kick, can result in all of these abnormal pressures, loss of circulation. Loss of circulation is primarily when you will have mud losses downhole. Effectively, what you are trying to gauge is, in a best ideal case scenario, the amount of mud you are injecting downhole is same as the amount of mud that is coming on the top. So there is no loss circulation. When you will have lesser amount of mud coming up to the top and more being injected downhole, that means you have a phenomena called loss circulation. That means your mud is getting pushed into the formation. It's not coming to the top. So these are all the different causes that can result in different type of effects. Primarily, loss circulation, abnormal pressure, and obstructions in the well bore can actually result in a loss of well, because if you have abnormal pressure, you can have a kick, which can turn it into a well blowout. If you have a well blowout, you can potentially have a loss of life, equipment, and property. You won't be able to recover that well. You may have to plug it off. That means all that money is now gone. And then this can result, a kick and a blowout can actually result in a hazardous operation with high pressure gas and oil coming to the top. So you have to recognize these warning signs, and you have to be cognizant that how you can actually take care of them. Directional drilling. Directional drilling is actually a science in which you actually deviate a well bore along a planned course to a subsurface target which is different or away from your surface location. And this could be a location which is different from your. So there is a subsurface location and there is a surface location. In directional drilling, your subsurface location is not going to be same as your surface location. So essentially, you are trying to access a resource which is away from your rigger point, and that is where the directional drilling actually happens. Why directional drilling? There are a couple of reasons, and I'm going to discuss those reasons in this slide. Number one could be site tracking, or the second one could be accessing inaccessible resources. You can see over here that the reservoir is in terms of a build-up area. We are trying to access it, this resource which you won't be able to access otherwise. Salt dome drilling, it's very difficult to drill through the salt dome. It becomes very expensive. It's not very feasible. So if your reservoir is on the side of the salt dome, then what you want to do is you want to come down straight and then access that resource. And then fault control. Sometimes because of the seismic activity, you cannot access that resource directly down because of there might be some seismic activity during these formations, through these formations. So to access this resource, you will come through the site, through the directional drilling. Sometimes you are trying to drill a relief well. That means you already had a blowout and just trying to relieve this pressure on this well or trying to kill that well, you will drill a relief well. And what will happen is that this hydrocarbon, rather than going straight, will start going through. You will be able to access this through the site tracking or site drilling or directional drilling. And then platform drilling. This is more feasible for the offshore operations, but we do it for the onshore operations as well, where you are doing platform drilling. So your platform will always remain in place while you will drill all these different wells. So you can actually access these resources without having to move your rig. And that is horizontal drilling. This is more common in the shale drilling, where you have a very limited or narrow shale formation. Imagine if you have to access this formation vertically, you will have to drill multiple wells to access it. Now, just by horizontal drilling, you can access the entire formation. And then multilateral. So you will have one main borehole, and then you will have side tracks in which you can actually access different resources without having to have a very big capital expenditure. Standard well profiles. Standard well profiles. There are different type of well profiles. We have discussed about the vertical section. You drill straight down. There are different type of other profiles as well, like S profiles, J profiles, and horizontal. Essentially, what happens is that in the S type of, you can see there is a rough S over here. You will have a straight section, and then you will have a build section. Essentially, build section is a curved section in which you are changing the direction of the well in a simple curve. It will have a 2 point. It will have a 2 points. There will be a end point, and there will be a specific target location. Or when I say end point, it is the end point of the straight section. So current endpoint as well as the target location. So it will have a combination of, so in the S type of profile, it is a combination of straight sections, build sections, tangent sections, and drop sections. And essentially what you are trying to do is access the resource which is not accessible vertically. Then in terms of the J profile, what actually happens is a combination of a straight section, build section, and tangent section. Tangent section is directly, as the name indicates, just directly tangent to the end or the target location. And then in the horizontal section, what actually happens is it's a combination of the straight, build, tangent, and second build section, as well as the horizontal section. What actually happens is that you will come straight down, then you will have a build section, so you will have a curved profile, and then you have a tangent section, which is straight, but it's tangent to from the target location of the build section. And then you will have a second build section, which is a curved section, and then you will have a horizontal section, which is a straight section. Historically, the reason for the ingenuity of directional drilling was actually not, the reasons were not straight. It was more for accessing property lines which were usually inaccessible. It is originally done for the unethical purposes, but people quickly realized the importance of these techniques, and uh, we actually owe the success of the shale revolution that actually happened in US to the horizontal drilling, because in the horizontal drilling we were able to access the shale resources which were previous to that were inaccessible. And then in 1934, a directional drilling was used to kill a wildcat well. This was done to drill a relief well, so you can actually drill a relief section and divert the flow of your hydrocarbons to a relief well rather than a wild well, so you can actually kill it. And that actually started the advent and beginning of controlled directional drilling in Conroe, Texas. Um, Deflection devices and techniques. Directional drilling is easier said than done. Over the course of time, there have been a different type of devices that have been developed, so you can actually drill uh, uh, directionally. Uh, Directional drilling can be done not only for side tracking, that means you are deflecting the well from your original course, but it can also be done for the trajectory connection or for the kickoff. That means you are trying to build an angle from the vertical to the desired direction. The first and foremost technique that has been used is called what we call jetting. It is used primarily in the softer formation. Essentially, what you do is that you use a bit with a big nozzle that is oriented to a desired direction, and you pump a high pressure mud through this nozzle. Effectively, what happens is that it will create the nozzle is at a particular direction. What will happen is that it will create what we call it will wash out a pocket. So this thing which you see at the bottom is called a pocket. Uh, and then you will drill a little bit, and then you will wash again, and then you will let that angle build up. So you will build that pocket through what you call a washout. And this has been done very successfully. It is still being done. But with the advent of positive displacement method, the jetting method is getting less and less used. It's getting obsoleted over the period of time. The other one is called open hole whipstock. Essentially, what happens is this is what we call a bottom hole assembly. Um, it is used in medium to hard formations where your rotary steerable or your PDM, which is positive displacement motor, we are going to talk about that in the next slide, are they won't be able to drill they won't be able to get the directional objectives. Essentially, what happens is there is this what we call a stab. So you will stab into the formation, and what will happen is that you will push your drill bit, and there is an incline section over here on which the drill bit will actually travel. But the angle of this incline section depends upon your trajectory. So there are these whipstocks with different type of angles. Uh, Essentially, what you want is that select a whipstock that will actually help you build the trajectory that you want. The drill bit will actually travel on that whipstock, and then it will come down at an angle. There is enough flexibility on the bottom hole assembly and your uh, drill collars and your drill pipe to get you that angle, and then you will be able to drill uh, at an angle. Initially, you will drill an undersized pilot hole. Then you will do, and then you will do one joint of drilling. Usually, one joint of drilling is around 20 feet. You will do the 20 feet of drilling. Then you will pull out of hole. POOH means pull out of hole. And once the pilot holes open up, you will repeat that process, and then you will make it a bigger. It is a very common technique that is used. I've seen it being used in offshore platforms, especially in Norway. It's a very reliable technique of directional drilling. And the final one is what we call PDMs, or positive displacement motors. They were first introduced or invented in 1960s by Danadrill. Danadrill was the first company that actually developed the positive displacement motors. Positive displacement motors is effectively a positive displacement pump just working in opposite direction. What actually happens is that it is a multi-lobal positive displacement motor. That means if you see over here, uh, you will have multiple lobes, while in case of a positive displacement pump, you will just have a single lobe. Effectively, what it does is that it converts the hydraulic power to mechanical power, and that is used to drive the bit. What effectively happens is that you will pump high pressure mud from the top. That high pressure mud will actually pass through the positive displacement motor, and it will rotate this rotor. And when it will rotate the rotor, this rotor at the end, in the most simplistic terms, is actually attached to a drill bit. When the rotor will rotate, the drill will rotate. And effectively, you don't need a rotating Kelly at the top. All you are doing is you are lifting your weight, so you have your bottom hole assembly, and then you are pushing it up and down, and the mud and the PDM is actually doing that work. So your string is kept stationary, you are only sliding it up and down. There is usually a bent sub, which is above the PDM. And this bent sub is actually providing a very important role. This bent sub can actually, and I'm going to show you in the next slide, this bent sub is actually able to rotate that bottom hole assembly. So all this assembly from the PDM down to your stabilizers and your drill bit, this bent sub will be able to move it at an angle. And it's very efficient way of drilling, directional drilling, compared to the contemporary deflection devices like jetting and whipstocks. And it is very commonly used now. It's just because it's easier to manage. It's not very. It reduces the time of drilling the well. It's more efficient in terms of jetting and whipstock, and so it is being used very commonly. The only drawback of this is that these mud motors, we call them mud motors or PDMs, they get worn down very quickly, and they are quite expensive to reline. So that's the only con of that. But the con of that actually outweighs the economical benefits of the whole PDM drilling, directional drilling operations, because now you can drill a well much more quicker than the well that is using jetting or whipstock. Rotating BHAs, effectively, you need stabilization along your borehole. So you will have full gauge of stabilizers, and between the full gauge stabilizers, effectively these are acting like centralizers. So between the stabilizers, you will have drill collars, and then at the very top, you will have your regular drill pipe followed by the heavyweight drill pipe. And I will discuss about what is the importance of the heavyweight drill pipe. So the location of the stabilizer gauge actually can result in either a very stiff bottom hole assembly or not so stiff bottom hole assembly. And we will talk about that in the next slide. So you can see in this video, you will have your vertical section, and then you will have your build section in which you will have your curved trajectory, and then you will hold, and then you will drill your tangent section. And once you have drilled your tangent section, you will drill your drop section. So the flexibility of your bottom hole assembly actually depends upon the stiffness. And usually the stiffness is calculated, the stiffness coefficient, it's a very generic formula, is your Young's modulus multiplied by moment of inertia. And your moment of inertia is pi times of your fourth power of your OD minus fourth power of your ID. That means the fourth power, the OD is the OD of your drill collars, and ID is the ID of the drill collars. And once you calculate your moment of inertia, and you will have the Young's modulus. So the Young's modulus is primarily based on the type of material. And based on that, you can actually have a stiffness coefficient. And I will not try to go deep into these calculations. Effectively, I will show you something over here. Uh, it is doing a stiffness calculation, a stiffness coefficient calculation of a drill bit or a drill collar, which is 8 inch in OD and 8 and a quarter inch in OD and 213 by 16 in terms of ID. Uh, so once you plug the OD into your moment of inertia formula, and your E is your Young's modulus of the material, you will realize that the stiffness coefficient is 6.73 multiplied by 10 power 9. And if you do the similar calculation for a 7-inch drill collar, you will find that the stiffness coefficient is 3.44 multiplied by 10 power 9. That means if you change your OD of the drill collar by inch and a quarter, that means 12.5%, your stiffness almost goes down by 42%. It's almost halved. So, and this stiffness is it's very important because it will determine the flexibility of your BHA. And the flexibility of your BHA will determine how much directional drilling or what is the angle of directional drilling you can actually achieve. Just an example, your side force. Side force is the force that is incurred when you have different type of drill collars. You can see just visually that the bigger the drill collar is, less flexible your assembly is. Less flexible your assembly is, you will have lesser of the side force. That means you won't be able to drill a lot directionally. And it will also result in a much more stiffer bottom hole assembly. But as you reduce the ODs of the drill collars, you will be able to achieve a much higher side force. Similarly, the other factor that actually comes on the flexibility is the weight on the bit, or WOP. So as I mentioned earlier, you have your drill pipe, your normal drill pipe, and then you have your heavyweight drill pipe. And your heavyweight drill pipe is effectively selected at how much you need weight on the bit. Because weight on the bit which will effectively change the ROP, or rate of penetration. And that will determine how quickly you can actually drill the well. PDM steerables, I talked about that there is a bent sub just above the positive displacement motor. This was actually developed in late 1980s. Bent sub can actually determine the angle that you will be able to offset. Lesser the offset is, lesser the component stress is, so you will be able to rotate without the concern of component failure. So usually you can actually either land your bent sub right on top of your PDM, or if you want more of an offset, then you can actually have a joint of drill collar, and then you will have your bent sub. And the closer you are deploy the bent sub to your drill bit, the lesser of the offset, and the farther you have, more of the offset you will be able to achieve. Types of drill bits. There are two major types of drill bits. Whenever you talk about a drill bit, talk to a drill bit guy, there are two major types. One of them is called roller cone bits. These are primarily for initially when we are drilling the intermediate casing or intermediate well, that is where we use the roller cone bits. Effectively, these are big rollers. They can have either mill tooths, that means these are just machine tooths with some surface hardening done to them. And then you can have tungsten carbide inserts. And effectively what happens is that they will just rotate and they will churn out the rock. And then there are fixed cutter bits as well, which are called PDC. These are more of diamond bit cutters or diamond infused, and then there are diamond bits as well. Unlike the roller cone bits, which are rotating all the time, that means your BHA will rotate as well as your roller cones will rotate. In this case, the BHA will remain, it is rotating, but the drill is rotating with the BHA. Essentially, there is no relative motion between BHA and the bit in this case. So roller cone bits and mill tooths are effectively steel tooths that are pre-milled and usually covered with a hard facing. So they can be nitrided. They can have some sort of a surface treatment to make them really hard. But effectively, these are very, very easy to manufacture. While in case of TCI or tungsten carbide inserts, you will have your drill bit, and then you will have inserts that are actually mounted inside the carrier. A roller cone anatomy, these are just some high-level components of the roller cone bit. You will have a API pin, which is effectively a thread connection at the top. This thread connection will effectively make up to the bottom hole assembly. Then you will have your leg. This is called shirt tail, which is just the end of the drill bit. And then you will have a nozzle. Now, this nozzle is primarily for injecting mud, but a bigger version of this bit can actually use for the jetting as well. And then in the end, you will have your. So with the advent of the positive displacement motors, they have proven themselves to be a very valuable part of the directional drilling. They are more commonly used now because of the reliability and high rate of penetration that they actually offer. With the PDMs, you can integrate them with the sensors, NWD and LWT tools, and it can actually help you evaluate the formation in real time, as well as drilling the formation at a much higher rate. They are very suitable for different type of formation and conditions, and I see them being used more commonly now. You will be able to drill medium and short curves, radius curves with the PDMs. Sometimes when you are trying to have a much bigger angle for the built-up section, then you might need a whipstock which is actually developed just for that angle. There is a range of radius that can be offered by the PDM. But with the help of PDMs, now we have actually reduced the bottom hole assembly component weights, your string, because the weight is directly proportional to your, you will be, by reducing the weight of your BHA components, you can actually have a much lighter string, which reduces the casing wear, which improves your string rotation and also reduces your string vibration. You do not want a BHA with a high vibration. And then there are, like with these, it has actually helped us in a couple of issues. Previous to the advent of PDMs, the bit life used to be very less. And then slide drilling or side drilling was becoming a big bit of an issue, but with the PDMs, we have been able to manage that issue. I think that's pretty much it. I will try to give you some time for questions. I know it was a heavy presentation, so I'm expecting some questions.